stud these with our hops and proteins. Now, rods and cones, or photoreceptors in general, have two different physiological phases. What they're doing when it's dark and there's no light actually hitting your photoreceptors of any wavelength whatsoever, and what they're doing when it's light, when there is a wavelength of light hitting your photoreceptors. So on this board, we'll do what's happening in the dark, and then we'll flip it up and do what's happening during the light on the other board. So you can consider this a photoreceptor in dark phase. So what's happening in the dark? All right. So we have to add a lot of stuff to our photoreceptor, obviously, to figure out what's happening in the dark. Now, what do we put on here first? Let's put a little sodium channel. Most important channels of a photoreceptor in the outer segment is a cyclic GMP sodium ligand-gated channel. What is cyclic GMP? It's just the ligand. Cyclic GMP is a molecule kind of like ATP. So ATP can turn into ADP, then A&P, adenosine triphosphate, diphosphate, monophosphate, and then it can actually have a cyclical form, which we call cyclical A&P. Well, cyclical GMP is the same pretty much thing, except instead of adenine as the nitrogen space, it uses quantity. Other than that, all you should really know is that cyclic GMP is a ligand. So it binds to a channel and causes it to open, just like any other ligand-gated channel. In the dark phase of these photoreceptors, cyclic GMP is bound sodium ligand-gated channels because there's always a high concentration of cyclic GMP. It's always being synthesized via enzymatic reactions that we will talk about upstream from opening these channels. So basically, the cell nucleus in the inner segment is constantly producing enzymes that are constantly producing cyclic GMP. So cyclic GMP concentrations are super high in the cells. Cyclic GMP is always bound to this sodium channel from the inside of the cell. Unlike an extracellular signal where you have a ligand bind to a channel outside to open it, in this case the ligand binds to the inside of that channel, causing it to open. Now when a cyclic GMP molecule, ligand, is bound to that sodium channel, what's going to happen? You're going to have sodium move through that channel, right? And as you know, sodium should move from outside the cell inside of the cell. We always know that sodium moves from outside the cell to inside the cell. That's just a constant, right? So a constant thing, sodium moving from outside to sodium moving inside. Okay. Now, make sure I keep on track here. We should probably put sodium potassium pumps on just in case. We know that sodium is going to move from the outside to the inside because we also know that we already have literally hundreds and thousands of sodium potassium pumps. Hydrolyzing ATP and putting 3 sodiums out for every 2 potassiums in. So we know that we always have a very high concentration of sodium outside and a very low concentration of sodium inside. And a very high concentration of potassium inside and a very low concentration of potassium outside. So when cyclic GMP is bound to this channel, it's going to cause sodium to come into the cell. Very simple. this is where things get slightly more confusing because we have to think about our graphs again. Let's just use -70. So we have a membrane potential, right? Remember our little action potential graphs that we looked at in A&P2? So basically, you have a resting membrane potential. And in nervous system cells, it's typically around -70 millivolts. So over time, if you monitor a resting membrane potential, you're going to be at around -70 millivolts. But remember what happens if you start allowing sodium to move into the cell? Because resting membrane potential, or your membrane potential in general, is charges inside minus outside equals your membrane potential. So if you start bringing positive charges inside the cell, what happens to the membrane potential? You bring positive charges inside, you are -70, and the membrane potential equals charges inside minus outside. The simple algebraic equation is going to tell you what's going to happen to this number. It's going to become more positive, right? Because you're bringing positive charges to the inside of that cell. So, if we had a little sodium ligand-gated channel and we opened it right here, so open channel, open Na plus channel, what's our graph going to start to look like? We're going to start to get an increase in membrane potential, right? Kind of like a graded potential and an action potential. And that's what this is. This is just a positive graded potential, right? Now, if you notice in the dark phase of our cells, we said that cyclic GMP is always in high concentration. We can even put a little concentration symbol with a little arrow so we know it's in high concentration during this dark phase. So during this dark phase, this channel is always going to be open. So what's going to be happening to the membrane potential all the time during the dark phase? This membrane potential is always going to be increasing, right? So you're going to have positive gradient potentials occurring during this dark phase. So because of channel open, positive gradient potentials always occurring. So you're never really at resting membrane potential during the dark phase. So we can write dark phase on here. Dark phase. Dark phase. So during the dark, that's important. During this dark phase, you're always going to have positive gradient potentials. Now remember what we called this photoreceptor again when we talked about different types of receptors. This photoreceptor we categorized as I know the terminology was stupid, but a separate cell, right? What kind of potentials do separate cells generate? They don't generate action potentials, they generate receptor potentials. Receptor potentials are basically just graded potentials, so any change in membrane potential that doesn't produce an action potential. This is the receptor potential. So the sodium moving through that channel creates the receptor potential. So that receptor potential is being generated during the dark phase. So don't come dark phase. So receptor potential generation occurs in the dark phase, right? Which is kind of odd, because you would think light's what's supposed to be stimulating our eyes, so wouldn't light be stimulating that? No, it doesn't. That's why we'll talk about what light does in this here in a second. Now, when we talked about neurons, the reason we could produce an action potential is because we had sodium voltage-gated channels. And those sodium voltage-gated channels allowed so much sodium to come in that they completely flipped the membrane potential from negative to positive, this is what an action potential is, completely flipping the charge of your membrane potential. These don't have sodium voltage-gated channels. That's why they can't produce an action potential. So they can only produce these graded potentials. But graded potentials are still important because graded potentials are often involved with secretions. Okay? So basically, when you get over to the inner segment has some channels that you should be partly familiar with. These were the same kinds of channels that you found at the terminal buds of your regular multipolar neurons that communicated with some type of tissue, effector tissue, via a chemical synapse, so not an electrical synapse. So these calcium voltage-gated channels, just like in a neuron, open up when the membrane depolarizes. However, in a neuron, that occurred because of an action potential traveling all the way down that long axon to the terminal bud. But these photoreceptor cells are very small. They don't have an axon that travels all the way down the body, so they don't need these rapid action potentials to transfer a signal to different places. So they can just use this receptor potential to change the membrane potential in order to stimulate these calcium voltage-gated channels to open. So these calcium voltage-gated channels open in response to the receptor potential, i.e. depolarization of the membrane. So these calcium voltage-gated channels open in response to the receptor potential. Now, just like a terminal bud of a neuron that innervates a tissue with the chemical synapse, you have synaptic vesicles or we'll call neurotransmitter vesicles. Doesn't really matter where you're going. At the terminal portion of this photoreceptor intersegment. And inside these little vesicles, you have a molecule that we call glutamate, which is a common neurotransmitter, especially in vision. All right? Now, you might remember how calcium was involved with the release of neurotransmitters in a neuron. When the membrane depolarizes, in this case via a receptor potential, it causes this calcium voltage-gated channel to open. What happens with calcium when this channel opens? Hopefully you remember. Calcium is almost always in very low concentrations inside of the cell because of things like calcium ATPase pumps that pump calcium out, or sodium-calcium exchangers that allow calcium to go out and sodium to come in via secondary active transport. But in general, calcium is always in very low concentrations inside of cells and very high concentrations outside of cells. So when a calcium channel opens, it causes calcium to come into the cell.